We're going to take a look at periodic trends with ionization energy for most of this video, and a couple of others at the end. So for ionization energy, a brief review is we are removing electrons from atoms. So we are turning them into cations. And to understand the trends, we are going to look again at Coulomb's law, where the attractive force is directly proportional to the charges over the distance squared. In general, if you take a look at your periodic table, you'll see that ionization energy increases from left to right. So if we look at sodium, magnesium, aluminum, silicon, all the way to argon, in general, there's an increase because we increase nuclear charge. So more energy is needed to remove the outermost ion. And you've seen that with photoelectron spectroscopy. The peaks shift towards higher ionization as we increase nuclear charge. There are a couple of notable exceptions, and these exceptions are most prevalent in row 2 of the periodic table. They exist somewhat in row 3, and they kind of disappear by then. But we're going to take a look at beryllium versus boron and nitrogen versus oxygen. For nitrogen versus oxygen, we're going to keep in mind that when we increase electron-electron repulsion, we decrease the ionization energy. And we increase electron-electron repulsion as electrons get paired within a single orbital. So let's take a look here at the electron configuration of beryllium. To the right, I have a PES diagram, and the black peaks represent beryllium. Now if I add an electron, I have boron. Boron will have a lower ionization energy because while the energy is shifted because of the larger nuclear charge, we're now removing from a p orbital instead of the 2s orbital. So it turns out that it's easier to remove an electron from a p orbital than its corresponding s, and ionization energy is less. The other exception I want to look at is between nitrogen and oxygen. So here I have the electron configuration of nitrogen with 3 unpaired electrons. And here in black, I have the PES diagram for nitrogen. When we add the 4th electron to the 2p orbital, now we have electron-electron repulsion. So for the 1s and 2s, increasing nuclear charge increases the ionization energy. For the 2p, increasing electron-electron repulsion pushes that last peak towards lower ionization energy. So it is easier to ionize from oxygen than it is from nitrogen. Moving down a periodic table, ionization energy goes down because the electrons are in orbitals that are farther from the nucleus. So if you look at a periodic table, you'll see that removing an electron from a 2s takes more energy than removing from a 3s, which takes more energy than a 4s, because the force of attraction is related to the distance squared. So it turns out that that distance is more important, and in this case for ionization energy, and so the energy level is going to really control what's going on. So let's take a look at the next slide. And here we have 9 different pairs, and you're going to decide the one that has the lower ionization energy, and you're either going to tell me it's because the outermost electrons are in the same energy level and the one with lower ionization energy has fewer protons, or the outermost electrons in the one with lower ionization energy are in a higher energy level, so they're further from the nucleus, or the one with lower ionization energy has more electron-electron repulsion. So pause the video and try to decide which one of these it's going to be for each of these 9. All right, let's take a look. If we're looking at aluminum and aluminum-3 ions, aluminum has its valence electrons in the 3rd energy level, aluminum-3 plus in the 2nd energy level because it has the electron configuration of neon. Also, the aluminum has more electron-electron repulsion. Going down, fluoride has more paired orbitals, so it definitely has more electron-electron repulsion. Also going down, potassium has electrons in the 4s orbital, while sodium is in the 3s orbital. So potassium's electrons are farther from the nucleus and easier to remove. And you can take a look at the others. Notice that calcium 2 plus and Cl minus have the same number of electrons, and so it is nuclear charge. And for the very last one, when we're comparing nitrogen or oxygen, that's the one that's the exception. Let's take a look at successive ionization values. So what that means is instead of removing the outermost electron from different elements, we are going to remove the outermost electron, and then the 2nd electron, and then the 3rd electron, and then the 4th electron, etc. And it turns out it's always going to be harder to remove the 2nd electron because there's a higher effective nuclear charge in the nucleus, because we're trying to actually remove something negative from something positively charged. But let's take a look at the data. If we look at the data, we see that there's a big gap in energy between removing the 1st sodium electron and removing the 2nd and 3rd. If we look to magnesium, we see the big jump is after the 2nd magnesium ionization. So it turns out that if we take a look at our PES diagrams, remember there's a big jump in energy levels? Well, that big jump in energy levels shows up in successive ionization as well. When we switch energy levels, we see a big jump in ionization energy. And seeing that big jump gives us clues as to how many valence electrons there are. So let's take a look at some possible data. Here I have 3 unknown elements, and I've marked where the big jump is. So for the first one, it's going to be a +2. It will make a +2 ion. It has 2 valence electrons. The second one, there's a big jump in ionization energy after the 4th. So there must be 4 valence electrons. And for the last one, we see a big jump after 2, which means there had to have been 2 valence electrons. So seeing that big gap tells us where the end of one energy level and the beginning of the next energy level begin. So I want to touch on 2 more periodic trends. Don't want to spend a lot of time on either one of these. Electron affinity is the tendency of a gaseous atom to gain an electron and become a -1 anion. That's not the same as electronegativity, which only happens when there are bonds between atoms. So most columns, it's a little vague, but there are some trends. First of all, we can see that it becomes more positive as we go down the alkali metals or as we go down the halogens. We can see that the fluorine is much more able to release energy, or it releases much more energy when it forms a fluoride ion than iodine does when it forms an I- iodide. We can also see that the noble gases, instead of being exothermic, are actually endothermic. We have to actually add energy to get any of them to accept an electron. And the last trend I want to take a look at is metallic character. If we look at the pictures towards the bottom of the page, we can see that moving from sodium across to chlorine, they become less metallic. And by metallic, we mean shiny and malleable and reactive with acids and conductive and all those different things. So we go from metals to metalloids to nonmetals. And we see that metallic character increases as we move from the top to the bottom of the periodic table. And column 15 shows this really well because it goes from nonmetals to metalloids to metals. So basically, if we're looking at these trends, we would see that francium is the most metallic and helium would be the least. So let's summarize what we've seen today. First of all, Coulomb's law can be used to justify periodic trends. The first ionization energy increases left to right across a period because of increasing nuclear charge, so increasing attractive force, but there are exceptions when we switch from s to p orbitals or we increase electron-electron repulsion by pairing electrons. First ionization energy decreases down a group because valence electrons are farther from the nucleus, and we know from Coulomb's law that means they are less attracted to the nucleus. So they are easier to remove. We've seen the definition of electron affinity, and we've seen that it often becomes less negative down a group, and for the noble gases, it is actually even endothermic. We have to add energy. And we've seen that metallic character tends to decrease across a period and increase down a group. I hope all of this was helpful. If you have any questions, let me know.